Okay, just have a look at page 18 of your gravitational field worksheet. We're just going to go through one calculation question. Right, so page 18, March 17, P42. Just have a look at that. Okay, so just have a look at that. Okay, now define gravitational potential at a point. Okay, so this one again is just something that you would have learned from last week. The definition is written in the notes. It is just work done per unit mass to bring a small test mass from infinity to a point in the gravitational field. Okay, so this one is worth 2 marks. You just say something about work done to bring test mass from infinity to a point. This is actually 1 mark. The other mark actually came from you mentioning per unit mass. Okay. Now, in the older past year questions, when they ask you to define gravitational potential, the answer might be slightly different. I mean, here you see it's written as work done per unit mass. In the older past years, for that same definition, they call it work done in bringing a unit mass. Okay. From infinity to a point in the gravitational field. Okay. From infinity to a point in the gravitational field. Okay. I know here I written work done in bringing a unit mass does not gain full credit. It's because their statement was just this. Okay, you had to write from infinity to a point, only then you get your full credit. Okay, the thing that I wanted to highlight to you is that sometimes per unit mass can be replaced as a unit mass. Okay, work done per unit mass, work done to bring a unit mass, they're actually the same meaning. All right, this one is more prevalent in the older past years. Okay, now then you should look at part B. You have a rocket that is launched from the surface of a planet and moves along a radial path as shown in this figure. The planet may be considered to be an isolated sphere of radius r with all its masses concentrated at its center. Point A is a distance r from the surface of the planet. Point B is a distance 4r from the surface. So you're looking at these points. Point A, distance of r. Point B, distance of 4r from the surface of this planet. All right. Now, show that the difference in the gravitational potential delta phi between points A and B is given by this expression, where delta phi is 3gm over 10r. Okay, so what you learned from last week was that there's actually two different equations, gravitational potential energy and gravitational potential. The first one that we learned was GPE, denoted by symbol U. It is negative gm m over r. Then the other one is gravitational potential, which is basically just GPE per unit mass, or rather it's U per unit mass. It will be negative gm over r. So they're asking for gravitational potential. We need to use this equation, specifically this one. All right. So if we try to find out what is the potentials at the respective points A and B, this one should be something like this. Okay, point A, potential at A will be negative gm over Ra. Potential at B would be negative gm over Rb. All right. Now your R is the one that you need to be a bit careful about. The R over here is the center to center distance between the masses. Okay. It's the center to center distance between masses. Okay, so here you notice that the question actually just gave you one mass. All right, but when they ask you to refer to points A and B, it's already understood that you will be placing a test mass at this point in order to test the point at that in order to test the point inside the field. Okay, so you actually have two masses here. So in terms of the center to center distance, your center to center distance for RA would actually be this one. This one is supposed to be your RA, which is R plus R, giving you 2R. If you're talking about center to center distance for RB, is the distance between the center of the planet and point B itself, where you place a test mass. This one is your RB. So this one will be R plus 4R, giving you 5R. Okay, so this is one thing you need to be aware of. What is your R? It is the center to center distance. All right, so from here, you already have the equation. Now, before you go any further, since you're talking about differences in potential, which is actually differences in scalar quantities, you generally will need to take higher value minus the lower value. In my case, I will actually say that potential at B is actually going to be higher than potential at A. Okay, so I take the higher value minus lower value, like what I mentioned last week. Differences in scalar, always take the higher value minus the lower value. So in your case, you take potential at B minus potential at A. Okay, so because I think I also mentioned this before, the larger the so-called height, the larger the GPE or potential. Okay, so if I'm going from here to here, you can actually say that your height is kind of increasing. Okay, that's why I can say that the potential at B is higher than that at A. All right, okay, so the rest is just basically just substitution and then doing algebra. So phi A is negative GM over RB minus with negative GM over RA. All right. Then after that, you know the GM is a common factor. Factorize it out, you get negative 1 over 5R plus 1 over 2R. Then GM becomes negative 2 plus 5 over 10R. And then finally, you will get the final answer as negative 3GM over R. Oh, sorry, negative 3G. You will get 3GM over 10R. All right. So this is your answer. Now for all this working here, it's only worth 1 mark. Okay, it's pretty simple substitution. Okay, so this one should be okay. I don't think there's any big issues with this. Right, then you go to the next one. This is where the bulk of your calculation marks come from. They tell you right now, everything. They are telling you right now that the rocket motor is switched off at point A. During the journey from A to B, the rocket has a constant mass of 4.7 times 10 power 4 kg, and its kinetic energy changes from 1.7 terajoules to 0.88 terajoules. For the planet, product GM is 4 times 10 power 14. It may be assumed that resistive forces to the motion of the rocket are negligible, and then use your expression in B1, what you've just done, to determine distance from A to B. Okay, so just to recap a little, what you just saw earlier was that you have this planet here, and then you have 2 points, points A and points B. Okay, so you are supposed to have a rocket right over here at point A initially. I think they mentioned that before. Yeah, the rocket is launched from the surface of a planet and moves along this path here. Okay, and somewhere along the way, it went through point A and point B. Okay, so from what the question described to you, they switch off the rocket motor at point A, and then once they switch out the rocket motor at point A, your rocket actually continue to move towards point B, but there are some changes that will occur. In your case here, you're going to have GPE increase because your so-called height has increased. And at the same time, your KE ought to be dropping because you will be slowing down. Okay. Here, actually, even if you didn't realize this fact, the question would have already told you about that. They already told you that as you went from point A to B, your kinetic energy changes from 1.7 terajoules to 0.88 terajoules. This is essentially dropping in KE. Okay, but how do I know that KE is dropping in the first place? I mentioned this last week when we were talking about escape velocity. If let's say you are at point A here, by right, you should have some gravitational force acting on your rocket, but your motion is in this direction, or rather your velocity is also in that direction. So when you have a force opposite to your motion, a resultant force opposite to your motion, you are actually going to be slowing down. Okay, your speed will decrease, so obviously your KE will drop. Okay, now from here, now that you know that there's these two energy, if you apply conservation of energy, you ought to be getting something like this. The change in KE is equal to the change in GPE. Whatever KE that has dropped would be the GPE that has increased. Okay, now in the previous part, in part B1, you are actually finding change in potential, not change in potential GPE itself. So this one, how do you relate it to GPE? You can make use of how potential was defined in the first place. Potential, just now I mentioned to you, was GPE over M, or rather it's U over M, so that you get something like, yeah. This one you don't substitute in the GPE, you just think it as it is. Potential at the point is equal to the GPE at that point divided by the mass, so GPE becomes mass times the potential at that point. And then you introduce the change symbol. Whatever change in GPE you have will be the mass times the change in potential. So this one is how you would find your GPE change. It will be now mass times change in potential, which is the expression in B1 here. Okay, your change in potential is already found in B1. Okay, so all you just need to do is to make use of this relation, sub in everything, and then find out one particular quantity, which is your R, right? So here, change in KE is change in GPE equals to mass times change in potential. So sum in everything, KE change, multiply with 10 power 12 to change from terajoules to joules. Your mass is 4.7 times 10 power 4. And then your delta phi is actually 3 GM over 10R from the previous part of the question, right? Then after that, you try to simplify it further. Still, your value of GM is already given here. Well, they never gave you the value of the mass of the planet. They did give you the product of G and M. So you make use of that. Okay. So sum in everything, you're going to get all these values. And finally, you're going to get the value for R. R is 6.878 times 10 power 6 meter. Okay. So just now it's already mentioned to you that for your case, maybe I draw something like this. You already know what is RA. And then you already know what is RB. So just now we know that RA was 2R. RB was 5R. So if they're asking you for distance AB, which is this one here, we know that distance AB by right will be 5r minus 2r. Okay, so it will be 3r instead. 3r. Okay, so DAB is 3r, then you get this, right? Now the one that I wrote here, 4r minus r, is actually based on just looking at this thing here. Okay, it's also the same thing, that you still be getting the same result. What I'm essentially doing was that this one was my reference point rather than the center of the planet. So distances AB would just be 4r minus r, giving me this distance. Okay, it's still the same thing. It's just that the approach is different, right? The distance AB is 3 times your value of r. So just sum that value in, and then you eventually get your answer as 2.06 times 10 power 7 meter. Yeah, and then you have it. Okay, so this one should be okay. This one is page 18. So this is how you use your equations for gravitational potential and gravitational potential energy. Okay, so this one is okay. Then we move on to page 5. Okay, so let's move on to page 5. Okay, page 5 would be November 15 P41. So let me just open it up. Okay, right. So if you look at page 5, this one should be quite straightforward. Okay, now you have a satellite of mass ms that is in circular orbit of radius x about the Earth. The Earth may be considered to be an isolated uniform sphere with its mass m concentrated at its center. Show that the kinetic energy EK of the satellite is given by this expression, where g is the gravitational constant, and then explain your working. So looking at what is being described here, you have a planet, and then you have a satellite whose mass is ms, and now you're moving in circular orbit about the planet whose mass is big M. Okay, so the radius of orbit they've already told you is actually x. Okay, so show that the kinetic energy of this satellite is given by whatever expression that you have here. Okay, now from what you learned in the previous lessons, we said that when something is moving in a circular orbit, say a satellite is moving in a circular orbit around a planet, there is something called linear speed, which is always tangent to the point where the satellite is at. Okay, so here, if they ask you for kinetic energy, you could have easily related to half mv squared. Okay, so you also learned before this that the linear speed for a satellite or any object that is in circular orbit would be square root gm over r. This is the general equation for linear speed, which is actually under, wait, I did not open the gravitational field notes. Let me just open up the gravitational field notes. It should be under page 6 of your notes, this one. Okay, so if you wanted to find the kinetic energy, you can just easily use you could just easily use half mv squared and then substitute in the expression for the linear speed. So in your case, this one would have easily just been gm over x. Okay, because you square already. This one, if you square it, it will just be gm over r. Okay, but your r is actually your x here. Okay, so this one would be the easy way to go about it. But you see, this particular question is 3 marks. I mean, you just did it like this, like the one that I just wrote on the screen, this one you get something like this. EK is half mgm squared. This one is the general equation. This one eventually you get gmm over 2x equals to EK. This one would have been your answer straight away, which is shown. Okay, but because you see your question is worth 3 marks, showing something like this will not net you your full marks. Okay, it won't net you your full marks. So how do you go about doing this? You need to kind of expand a bit further. You need to explain the story a bit further behind. Just here, they already told you to explain your working. Okay, so if you wanted to do this particular way, which is somewhat easier, you probably have to do it this way first, where you first say that gravitational force provides the centripetal force. Then after that, you will have Fg equals to Fc. You will get Fg equals to Fc, which in turn will be gmmx equals to mv squared over x. So you get v equals to square root gm over x. Then your ek is half msv squared. So you're going to get half msgm over x. Then the final product is gmms over 2x. Okay, right. Will the linear speed equation be in the formula sheet? I don't think so. Your formula sheet is actually just this equation that you see here. Okay, linear speed. Your formula sheet is just this one page. Okay, it doesn't, and it's actually a combination of equations from AS and A2. So to answer your question, no, it's not inside. Okay, A2 physics will have quite a number of equations that you need to memorize or understand. Okay, yes, you had to memorize quite a fair bit. There's quite a lot of equations in A2 physics that you will need to memorize, and all of them are like, how to say, in a way new to you lah. Okay, in AS, the equations that you see are kind of familiar because you have seen them before in IGCSE. But when you go to A2, the equations that you start to see are pretty strange. I mean, strange in the sense that you've never seen them before. Okay, but given time and practice, you will eventually notice that they're actually quite straightforward. I mean, all right. So just slowly digest the information. Okay, so if you wanted to do this one, in your case, you wanted to follow the easy and understandable way of answering this question, this one would be your method. Okay, this I would recommend doing this one. Okay, I would recommend doing the ones that I circled in blue here. Okay, this one is something that people can easily understand. Okay, yeah, this one also, I think I forgot something on the right hand side. This M is actually supposed to be ms. Sorry, I remember to change one of the variable, but I forgot the other. Okay, so this one is how you will get your full marks. All right, if you had just shown this one by itself, you will not be getting the full mark. You will have to show the workings that I've circled in blue right over here. Then you will get your full marks. Okay, now there's also another way of doing this, but I think this one is actually pretty complicated. I mean, not as straightforward because this one relies on you doing something like this. It's something like algebra manipulation, where you say Fg is equals to Fc. So you have gmms over x squared equals to, yeah, here also I forgot something. This one is a square. My mistake, sorry. There's a square here. Okay, so back to the one on the left, GMMS over x squared, giving you MSV squared over x. Okay, so if this one is more like a case of you just simplifying things, where you get something like this. If you simplify this, this one will become GMMS equals to MSV squared. The x here will cancel off one of the powers here. So this one will become GMMS x equals to MSV squared. Then after that, what you're trying to do here is that you're trying to make this form into half mv squared. So this one would mean that you need to multiply by half on both sides of this equation, which in turn becomes GMMS over x equals to half MSV squared. So this one already is actually your EK. Therefore, so here you probably write this. Since EK is half MSV squared, therefore EK is GMMS over x squared. So this one is shown. Okay. Okay, I've also done it in this manner. Okay. Not forgetting, you also still need to write the statement now. Gravitational force provides your centripetal force. Okay, you can write it like that also. But as I mentioned, now that you've seen both workings, the blue color one is actually somewhat more straightforward to do compared to the second method that I just showed. All right. Okay, so this one should be okay. Now, for the second part of your question, they ask you, state an expression in terms of G, M, Ms, and X for the potential energy EP of your satellite. Okay, what would be the potential energy of your satellite that is now orbiting around your planet with mass M? Okay, what is the GPE at this point? So we know that GPE is negative GM M over R. This is the general equation. So applied to this question here, your R would actually be your X, because the question defined your center to center distance between the masses as X rather than R. So your potential energy EP would actually just be, let me get rid of this. Your potential energy EP would just be negative GMMS over X. Okay. Yeah, and this one, your small mass M is actually your MS, no? All right. So negative GMMS over X. So as I mentioned to you, gravitational potential energy, because it's a scalar, if you have negative sign, it's actually an indication of your value. You need to have it inside all the time. Okay. So this negative sign must be inside. Otherwise, it will be marked as incorrect. Okay, so that one is for this. All right, then we go on to part 3. Now, part 3 is telling you, using your answers from 1 and 2 above, which is this one and this one, find out the expression for the total energy ET of your satellite. Okay, what is the total energy ET of your satellite right now? Okay, now when your satellite is, okay, now let me just erase everything. Your planet, your satellite, moving in circular orbit. When your satellite is moving in a circular orbit like this, it will have GPE, it will have KE. Now it has KE because it is moving, it has motion. In the first place, we already see that it has linear speed. V. So it must have kinetic energy, which we already found out as GMMS over X, over 2X, sorry. Then after that, the GP we also already know, which we already found in the previous part of the question, which is negative GMMS over X. Okay, so your satellite here actually has two components of energy, KE and GPE. So if you want to find total energy, you just add them up. So total energy is thus EK plus EP. So you add up the values that, or rather the expressions that you have for both, you're going to get this GMMS over 2X plus with negative GMMS over X. So you simplify the algebra, you're going to get this negative GMMS over 2X. Just like that. Okay. Right. So that one should be fine. Okay, the last part will be something like state and explain question. All right. The next part of the question is actually asking you this. Small resistive forces are acting on the satellite, causing the radius of the circular orbit to change. Use your answers in A to state for the satellite whether each of the following quantities will increase, decrease, or remain constant. Okay. So if we go back to that same situation with the satellite, this one, I think there's no need to do any complicated calculations. Just some simple common sense will actually help us to deduce the answer. So we know that our satellite is in circular orbit, is moving with certain velocity v, linear speed v. But now they tell you that your satellite, as it is orbiting, it is encountering resistive forces of R. So what do you suppose would happen to the energy of the satellite? Okay, bear in mind that we're not talking about total energy of the system. Okay, we're talking about energy of the satellite itself. So here, common sense will tell you if your satellite is moving and encounters resistive forces, you need to have work done to overcome the resistive forces. Work is done by the satellite to overcome resistive forces. So energy must have been lost here. Your total energy of the satellite must therefore decrease. Okay? So it's important to realize that you're talking about the satellite itself, not the system. If you're talking about a system which consists of two different bodies, total energy remains the same. But here you are actually talking about one object inside your system, which is the satellite itself. So total energy is decreasing. It is not constant. If you're wondering what I'm talking about, you can think of it this way. If I tell you total energy is actually energy of object A and energy of object B, by conservation of energy, E total is constant, but EA and EB can change. Okay, what I mean by that is that, say for example, total energy is 100 joules. EA, EB, maybe this one is 80 joules for EA, EB is 20 joules. So if EA suddenly drops to, say, 30 joules, this one will increase to 70 joules, so that the total still remains at 100 joules. So in our case here, when you're talking about the satellite, it's kind of like you just talking about a component inside the system. Okay, so that's why I can say the energy is decreasing. Okay, just to make this distinction clear. All right. Okay, so total energy is decreasing. What would we then say about the radius of orbit of our satellite? Now, common sense again will tell you if the satellite is having less energy, obviously it cannot stay high up in orbit. It will have to come down to a lower radius. So answer is that it will decrease. So that one is okay. Then what about the potential energy? Yep. Wait, why? For part 2, why radius of orbit? Your satellite has less energy already, right? It has less total energy. In order for you to orbit, you obviously need a lesser height. What? Okay, my common sense tells me that lah. All right, my common sense is telling me that if the total energy decreases, I cannot stay high up in orbit. My radius is going to decrease. But if you want something like a mathematical proof for that, yes, I can show it to you. That one is at the bottom part. I can show it to you later on. All right. But this for now, this is the simplified answer. There's a complicated answer which you might want to see. Okay. Okay, so total energy decreases, so the radius of orbit will decrease because that is common sense. You want to go higher up in orbit, you obviously need to have higher total energy. If you are losing energy, your orbit will be lesser. That is common sense now, all right? But there's a mathematical proof for it. I'll show it to you later. Okay, so if you look at part 3, potential energy, if your radius or height is lower, obviously your potential energy must be decreasing. Okay, this one is number 1. So this one is the answer, potential energy decrease. And then what about if you're talking about your kinetic energy? This one, you can use conservation of energy. If one energy drops, which is GPE here, the other energy, which is kinetic energy, must increase. So kinetic energy increases here. Okay, so this one should be fine. All right, so far so good with this. This one is if you use common sense lah. The reason why I'm trying to use common sense here to explain this is because your question here is just asking you to state. They didn't really ask you to explain. If you wanted to explain, it'll be a bit more complicated to explain actually. That's why here the question just says state only. They didn't really ask you to explain. Just state what happens. So the easy way to go about in stating what happens is to look at it from a common sense kind of approach. But if you want to look at it from a mathematical kind of approach with equations and all, yes, you can. Yes, kinetic energy here refers to the kinetic energy of the satellite. Yes. Whatever energy that you're talking about here refers to the satellite only. Okay, the keyword here is you are only supposed to look at the satellite. Okay. Right. So far, so good. Conservation of energy, what? I mean, you get conservation of energy that if GPE drops, KE must increase, what? That is, again, common sense law. But okay, if that one does, yes, but total energy drop. Total energy of the satellite drop. Okay. Okay, now, if that one is not convincing enough, okay, we just look at let's just look at the very mathematical treatment of the situation. This one is the ones that I just written in red. Okay, this one is if we use equations. All right, so let's just go through with that. All right, so maybe this one is more your cup of tea. Okay, now for part 1, we want to explain why total energy decrease. Okay, so if we try to explain why the total energy will decrease, this one I can say that when you do not have resistive forces, your total energy, which is the sum of K and P before and after, will be the same. But now when you have resistive forces, this one was talking to you about when you have before resistive forces. This one is talking to you after you have resistive forces. Okay, so the total energy that you have here is before resistive forces. Then the right side here is after you have resistive forces. So here, your total energy of satellite here would have to take into account work done against resistive forces. So now your final total energy is actually your initial total energy minus resistive forces, therefore total energy decrease. Okay, so this one I think should be okay. This one is something like conservation of energy again. Okay, so this one is all right. It's basically talking about energy before and after. Energy after must take into account work done against resistance, so final energy is going to be less than initial energy. No? Okay, so this one is okay. All right, now then after that, we go through the other equations. Let me just write down all the equations. Just give me a second. EP is because of the negative sign. The negative sign is the one that causes a lot of issue. EK is this. EP is negative GMMS over X. E total is negative GMMS over 2x. Okay, these are the three energies involved here. Okay, so what did I write in number 2 from A to this one is what I wrote. Number 2 is also something to explain total and why total energy is less. Oh, okay. Now I look at my old explanation again. This one is one way of explaining why total energy drops. This one is also one way of explaining why total energy drops. Yeah, this one is just another different way of doing things. Your satellite is here. You have linear speed V. You have resistive force R. Okay, so when resistive forces is present, your tangential velocity or your linear speed obviously would have to drop. This one is something that we all can agree on. The moment you encounter resistive force, your speed will drop. Okay, so when your speed is dropping, your centripetal force required to maintain circular orbit will also drop. Therefore, radius x decreases. Because you see, Fc is actually mv squared over r. Then after that, or rather Fc is mr omega squared. If I say that r drops, centripetal force. Oh, okay, yeah. Tangential velocity drop. Okay, it's because of this. B drops, Fc drops. Then after that, when Fc drops, R should drop. Because here the relation was Fc is proportional to V squared, Fc is also proportional to R. Okay, so when my velocity drop, my centripetal force drop. And coincidentally, when my centripetal force drop, my radius will drop. This one is explaining why radius x decrease. Yeah, this one, all right. This one is talking about how your radius x decrease. Just now you're asking me this one, right? This one, right? Radius of orbit, because I told you total energy decrease, the radius will obviously be lesser because you cannot maintain orbit as high up. If you want some other way of looking at this one is actually the answer, okay? Because you have resistive force, your linear speed will drop. When linear speed drops, you will agree that centripetal force to maintain your orbit would have dropped. So when your centripetal force has dropped, your R would drop too low. So that's why your radius x decrease. Okay. So does this sound better rather than using the common sense one? Okay. So this one also will tell you that same story. Now it's because of this also that you can actually also work out that your total energy is dropping. This is where your negative comes into play. You see, your total energy is negative GMMS over X. Okay. So you just think of it this way lah. If I tell you that you had GMMS over X itself, this one is your value, or rather magnitude lah, okay. Say I tell you that GMMS over X is equals to, say, magnitude. When you already establish that X is dropping, this whole expression will actually increase. So your magnitude is increasing. So far so good? Can you get the concept here for this one? If you just don't bother about the negative, you just look at the GMMS over X. If X drops, that means the whole expression over here will increase. All right. Now, that would mean something like this. If originally before I give you some test values, before this, your value was maybe say 15. Then after this, because your X drop, your value now becomes say larger at now 30. This one, you can easily tell me that value has increased. Okay, this one okay. But the problem is your total energy here has a negative sign. So if I try to put in a negative sign here with negative sign, that will mean that before it is negative 15. Then after that, when my X has dropped, remember I told you the magnitude will increase, but once you consider the negative sign inside, it becomes negative 30. So from negative 15 to negative 30, this one is actually value decrease. That's why I can say that my total energy here is dropping. It kind of ties back with what you have in the first explanation now. Okay. So this one is also trying to explain to you why total energy is dropping. Okay, then after that, you want to talk about EPE, why EPE is dropping. You again use back the equations for EPE. Let me just wipe off whatever I have here. Your EPE, or rather your EP, is having that same issue, negative GM S over X. So by right, if your X has been established to drop, we know that your magnitude is going to increase. This one here is what I will refer to as my magnitude. Okay. So from here, it's the same thing as before. If before my value was something like negative 15, then after that, when my X has dropped, my magnitude no doubt is increasing. But because I have a negative sign there, the conclusion is that my value is decreasing. So that's why my EPE value here, I can say it as decreasing. This one is if you try to look at the equation itself, and then you take into account the negative. When X is dropping, I know my magnitude increase. But after taking into account the negative, it's actually telling me that my value is decreasing even more. Okay. You can also do something similar to kinetic energy. This one, if you do not want to use conservation of energy, you just want to look at the energy equation itself, which is this one. Now, this one will be pretty straightforward because there's no negative sign. You see, only EP and ET had negative sign. But for EK, the kinetic energy, this one is more straightforward. This one, if your X is dropping, we know that your magnitude increase, because there's no negative sign, you can also just say that your value is increasing. So kinetic energy increase. Okay. This one is just by you looking at the equation itself. All right. So now notice how convoluted the explanation becomes when you try to explain all this with the negative sign and all, and looking at the equation. That's why I just try to simplify it by using common sense. But yeah, if the common sense doesn't really seem to gel with you that much, maybe the equations would be better. All right. Okay. Right. Okay. So this one is okay. Then we go to another question. We were doing page 5. We did page 18 already. Okay, then the next one would be page 33. Okay, right, page 33. This one I think should be okay. Not so much calculation based on something else. Okay, just have a look at, say, page 33. March 19, P42. Okay, so let's go through that. March 19, P42, question 1. Okay, define gravitational potential. I think this one we can skip. It's something that we just done before. So work done to bring work done per unit mass to bring a small test mass from infinity to a point in gravitational field. So this is a definition from your notes. Okay, now what we want to look at is part 2. They're asking you use your answer in 1 to explain why the gravitational potential near an isolated mass is always negative. So as I mentioned to you just now, GPE value is going to be negative GMM over R. Potential would also be negative GM over R. So it's always important to maintain the negative sign there, because it's telling you that the value is negative. It's always going to be below 0. So your past year questions actually will ask you to explain why were they negative in the first place. Okay, so this one kind of relates to what I explained in the notes before. If I tell you that this one is an infinity, and then this is the point I'm considering, that is at, say, a distance of r from your planet. So what we want to know is what's the GPE value at this point, knowing that the GPE at infinity is 0. So, or rather, because we're doing potential, let's talk about potential. Potential at infinity will also be 0. Okay, so we're interested in what is the value of potential at this point here, a distance r from your planet. So because we already defined gravitational potential as this, you see, in the first place, work done to bring a unit mass from infinity to a point inside the gravitational field. So assuming that we have a test mass, a unit of mass that we want to bring over to this side, in the first place, we already know that the mass would experience a gravitational force. Because it's inside the field, the gravitational field of this big planet. So if we were to bring it from infinity to this point, we actually don't need to purposely apply any external force to push it from infinity to this point here. The mass by itself will start to move because of the existing gravitational force on it. So this one, as I mentioned to you, is where we will say something like this. Let me use a different color. What kind of color can I use? Some kind of orange now. If I bring it from here to here, we will say work is done by mass. The GPE, or rather potential, decreases from 0. Therefore, GPE, or potential, is negative. Okay, so because here my GPE is 0, I go towards the left, the GP is dropping. I will end up with a negative. Same thing also can be said for potential. At infinity, potential is 0. If I go towards the left, towards the point here, my potential is dropping. So I'm dropping from a 0 value. So my potential would also be negative. So usually this kind of question, the standard answer will usually be these statements that you're seeing here. It comes out quite a fair bit, and usually is allocated 3 marks. So for those 3 marks, there will usually be 3 statements, important statements that you need to write. You always need to first say, where is your potential defined as 0? Gravitational potential at infinity is defined as 0. This is number 1. And then you also need to state the nature of the force acting on your mass. Gravitational force is attractive. Now, because gravitational force is attractive, it's from here that you will able to deduce that work must have been done by your mass in order to move from infinity to the point, because the gravitational force is what's pulling your mass right now. What is done by the mass as it's brought from infinity to the point, which causes decreases in potential. Okay, you actually don't need to write potential energy because you're talking about potential. So if you want to write something else from here to make your answer feel more complete, potential decreases from 0, therefore potential is always negative. Okay, this statement is actually not required because it's actually a repetition of your question stating why potential is negative, but it helps you to see the complete story. Okay, so you have to always write these 3 statements. Gravitational potential at infinity is 0. Gravitational force is attractive. Work will be done by the test mass as is brought from infinity, causing decrease in potential. So therefore, your potential will always be negative. Okay. So this one is one part, just like that. Okay. Then after that, we go on to the next one. So let me just erase off whatever I do not need here. Okay, so then the next one is talking about calculation. This one, I think we can just quickly do the calculation. It's something pretty straightforward. Okay, now your question here tells you that you have a spherical planet of mass 6 times 10 power 24 kg and a radius of 6.4 times 10 power 6 meter. Okay, a satellite of mass 340 kg is in circular orbit about the planet at a height of 9 times 10 power 5 meter above its surface. Now for your planet, for the satellite, show that its orbital speed is 7.4 times 10 power 3 meter per second. They want you to show that the linear speed is that value here. Okay. Right. So just now, as I mentioned to you, if you're talking about linear speed is always square root gm over r. And this is the thing that is orbiting. This one here is your linear speed, v. Okay. So there's one thing that you just need to be a bit careful. Yeah, orbital speed is linear speed. Okay. Now, one way in which you can know they're talking about linear speed is that you just look at the units. It's meter per second. It's talking about this. They're not talking about angular speed or anything like that. If you see it's talking about angular speed, angular velocity, then you will see a hint that from the units, it will be in radians per second. Okay, but since you see it's meter per second, you already know it's talking about linear speed. Okay. Orbital speed in a way can actually kind of mean your linear speed or angular speed. All right, but here how you know it's talking about linear speed is because you see they're talking about it's because you see that in the units they're talking about meter per second, so you know it's linear speed. All right. Okay, so if you want to find the linear speed, because this question is only worth 2 marks, it's actually already just sufficient for you to do this. Where you just straight away use the equation for linear speed and then sub in your values. But here you need to be careful a bit about your distances r. So by now you should know that your distance r is actually supposed to be the center to center distance between the masses. This one should be your distance r. Okay, this one is your distance r. It should be the center to center distance. All right. But what you have here, given inside the question, when you see that the satellite of don't know or of mass 340 kg is in circular orbit at a height of 9 times 10 power 5, this one by itself is not your r. You see, is at the height above your surface. I mean, if you try to visualize it, it is actually talking about this. If this one is your planet, the green colored section that I just highlighted is your surface. Your satellite is actually 9 times 10 power 5 meter from the surface. That one will not be your r, because r must be center to center distance. So to find the center to center distance, you actually have to take into account the radius also. Here they already give you the radius, 6.4 times 10 power 6 meter. So your r must be these two added together. That's why you see the equation where for r is these two added. Okay, so remember to add them together. That one will give you your r. Your value of g and your value of m, this one is pretty straightforward. You know the values for the question as well as for the data sheet. Just do your multiplication and division and then remember to square root it. You're going to get your answer as 7.4 times 10 power 3 meter per second. Okay, right. So in your case, just showing this would be enough. All right. But you notice that in my case, I kind of actually derive everything out to show what is the linear speed. This one is also possible, but I would normally do this if the marks given is maybe 3, and then after that they suddenly tell you a statement, explain your working. If I see something like 3 marks allocated and then they say explain your working, I would have to do the ones that I'm circling in pink here. Okay. So what I have here is actually kind of like overkill, but I have a habit of doing this for all my questions because I always start from the derivation first to go to the final answer. Okay, but I tell you first now, all right? Whether you are going to do the equation straight or you have to derive it, kind of depends on what the question is saying and how much marks is allocated. All right. Okay, so this one should be okay. Then other than there's another part in the following section. So let's go to the next one. Then from here, they ask you calculate the gravitational potential energy of your satellite. So it's kind of like what we just did, but this one they give us actual values to submit. Your gravitational potential energy of your satellite by right will be U equals to negative GMM over R. So your G, you know, your big M, you know, your small m, you know, your R, as I mentioned to you, is you adding the radius and the height together. So once you do the necessary calculations, you're going to end up with the answer as negative 1.86 times 10 power 10 joules. Okay. Yeah, and another thing to mention is do not omit your negative. Your negative is important. This is something that your marking scheme will tend to look at when it comes to calculation of GPE. Okay, so that one is fine. For part C, rockets on the satellite are fired for a short time. The satellite's orbit is now closer to the surface of the planet. State and explain the change, if any, on the kinetic energy of your satellite. What happens to the KE now? Okay, so in your case, you want to explain what happens to the speed because you want to explain kinetic energy. So how would you go and relate the speed with your radius? Because they tell you that your satellite orbit is now closer to the surface of the planet. That means R is dropping. So you can make use of what you just did earlier, where you say that linear speed is square root gm over r, so that v square is actually inversely proportional to r. When your r is smaller, your v is greater. Therefore, kinetic energy increases. Just like that. Okay, so this one is okay. All right, then next question should be on page 30. Okay, wait, let me just have a look at page 30. Okay, right, so this one is okay. I'll move on to page 30. Okay, just have a look at page 30. This is the next question. Right, so if we look at page 30, it's still talking about potential again, but this time we are talking about something a bit different, explaining why potential is going to be constant. Sorry, not June 18. We want November 18 P41. Okay, so what is gravitational potential? We're just going to skip that because we've already gone through two of these kind of questions before. What we want to look at is part 2. Suggest why for small changes in height near the Earth's surface, gravitational potential can be considered to be approximately constant. Okay. Now, why can we say that potential is going to be constant for small changes in height near the Earth's surface? All right. All right. This one is more related to the equation itself. We know that GPR potential is negative Gm over R. So let's consider a planet like what we have here, drawn here. This is a planet. If you're talking about the surface of the planet, maybe I zoom in just to get zoom in. If you're talking about the surface of the planet, right over here, let's assume that your center to center distance is going to be R, between the center of your planet and the surface that you're considering. So let's call this position A. Now, if we have small changes in height near the Earth's surface, that would mean that we have to go a short distance of h. So let's just say that we go a short distance above the surface of the planet, a distance of h. We now end up with point B. Okay, so what we're interested in is point A and point B. Now, for position A, our potential there will be negative Gm over R. At position B, our potential there will be negative Gm R plus H, because we want the center to center distance. Our center to center distance will actually be this one, R plus H. Okay, now, because in the first place we're talking about small changes in height, because H is so much smaller compared to the radius of your planet, compared to R, this one is your radius of your planet. Okay, because your height that you consider is so much smaller than the radius of your planet itself, we will actually be able to say that R plus H is actually the same as R itself. Okay, what do I mean by that is, if let's just say I give you a certain value to look at. Let's just say H is just 1 meter. but I tell you R is 1 million meter. So if I ask you R plus H, it will just be 1 million and 1 meter. Okay. If I try to go and write them out in scientific notations, R itself was already going to be 1 times 10 power 6 meter, okay, 1.00 times 10 power 6 meter. So R plus H, if I go and write it in the same form for the scientific notation, it's just going to be 1.00 times 10 power 6 meter. This little one that you have here is not even going to register. That's why I can say that R plus H here will be the same as R itself if H is so much smaller than your R. Okay, so if your R plus H can be considered as the same as R itself, this equation here, negative Gm over R plus H, can actually be the same as negative Gm over R. So you do a comparison between these two equations, they're actually going to be the same. Therefore, phi is constant. Okay, that's the understanding here. Why we can say that your potential is approximately constant for very small distances above the Earth's surface. All right, this is you explaining from an equation point of view. All right, so your answer will be something like this, where you say here, phi is negative Gm over R, gravitational potential phi is inversely proportional to your radius R. Now, near the Earth's surface, change in height is very smaller. Yeah, near the Earth's surface, your change in height H is very much smaller than radius R. Okay, it's very much smaller. You need to have the keyword R. You need to have the keyword much smaller. Thus, R is approximately constant. So phi is approximately constant. Okay. This thing here would only make sense if you have this diagram to kind of refer to. If you just look at the explanations by itself, it kind of doesn't make sense. It has to be related to this diagram. Only then does it make sense. Okay. So if you're talking about near the Earth's surface, change in height H is very much smaller than R. Thus, R is approximately constant. Therefore, phi is approximately constant. Okay. So this one is one way of explaining this. There's also supposed to be another question that I was planning to do with you today that explains to you why gravitational field strength is constant near the Earth's surface. But this one, I think I have to leave it for the next lesson. Okay, but never mind. We can still finish off part B here at the very least. Okay, so part 2 I think should be okay. Then we move on to part B. All right, now for part B, this one is talking about escape speed, which we just did towards the end of the last lesson. We tell you right now, the moon may be considered to be a uniform sphere with a diameter of 3.5 times 10 power 3 kilometer and a mass of 7.4 times 10 power 22 kg. A meteor strikes the moon, and then during the collision, a rock is sent off from the surface of the moon with an initial speed v. Assuming that the moon is isolated in space, determine the minimum speed of the rock such that it does not return to the moon's surface. Explain your working. Okay, so what the question here is basically trying to mention here is that you have a moon, a meteor strikes the surface of the moon, causing a rock to be sent flying off. Okay, now they want you to find out what was the minimum speed of the rock so that this rock can just keep on flying off to infinity and not return back to the surface of the moon due to its gravitational pull. So this one, you know, is talking about escape speed. they want the escape speed here. Okay. So your goal here is to find out the escape speed. Now, because I see that this one is 3 marks, and then I see that you have explained your working, I don't feel it's something that you would, I don't think it's wise to just straight away sub in your escape speed equation. Okay. You just straight away sub in your escape speed equation. This is what you're going to end up getting. All right. But so for your case, I think it'll be better to just derive it out. Okay. So in my case, you notice that the working here is deriving out the escape speed equation. So the derivation last time I mentioned to you, as your object is trying to escape, you have losses in KE as well as gain in GPE. So they're interrelated with each other through conservation of energy. You will have half mv squared minus 0 equals to 0 minus negative gmm over r, eventually giving you v equals to square root 2 gm over r. All right. So from here, you just sub in your values that you know from the question. V is 2 times g times m times r, divided by r, sorry. Your r here is actually 3.5 divided by 2 because you are given the value of diameter. So you need to divide by 2. And don't forget to change your units to meter. So from here, you will eventually get your answer as 2.38 times 10 power 3 meter per second. This is your escape speed. Okay. Right. Yeah, from what the marking scheme actually indicated, it seems like you actually don't need to derive it because from what I can see, this one is a B1 mark. The B1 mark actually is you writing this equation for escape speed. Your C1 mark is you subbing in the correct values. Your A1 mark is you having the correct answer. So in your case here, actually, even if you didn't derive it and you just start off with the equation, you will still get your full marks. But for me, most of the time, if I see that the marks allocated is quite a lot, and then they have that little statement explain your working, I tend to go through the derivation from the start, just in case.